This is a practice question on free fall. We always start our practice problems by writing our three equations of kinematics. Final velocity equals initial velocity plus acceleration times time. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. We read the question. Astronauts on our moon just must function with an acceleration due to gravity of, so our acceleration is 0.150 Gs. Well, G is 9.81. And that would be meters per second. Okay. If an astronaut can throw a certain wrench 9 meters, so the displacement becomes 9.00 meters vertically up on Earth, how high could he throw it on our moon if he gives it the same starting speed in both places? Okay, so what we have is we have an astronaut throwing an object on the Earth, and then throwing the same object on the moon, which has much less gravity, seeing how high it can go. Okay, so this is our displacement on the Earth, and we're looking for displacement of the moon. Okay, so first off, let's look at acceleration. Acceleration on the moon is 0.150 times gravity. That's what the G stands for. And we're going to make gravity down, which would be negative, so that becomes a negative 9.8. Now, why did I say what's my initial velocity? Because it says that when the astronaut throws the object on the Earth, he can throw it 9, and it says how high can he throw it if he gives it the same starting speed. So it's a huge clue that we need to find what that starting speed is. That's why I wrote the initial velocity. So if I'm going to throw a wrench on the moon with the same initial velocity I had on the Earth, what I need to do is I need to find out what is that initial velocity. So I'm going to try and find the initial velocity that I threw the object or the wrench on the Earth, and then I'm going to use that to find my distance or displacement that the wrench will go on the moon. Okay, so we need to match these up with one of these. Now I'm going to put another variable over here that we know, gravity, which will be the acceleration on the Earth, because remember this is acceleration on the moon, is just a negative 9.81 meters per second squared. Okay, so if I look over here, I have final velocity, which I don't have over here. I have initial velocity, which I'm trying to find. I have acceleration, and we are trying to find the initial velocity of the Earth, so we're looking at the Earth values. So I have that, and time, I don't have that. So let's look down here. I don't have VF. I'm trying to find VI. I have my acceleration due to gravity, which is this negative 9.81 on the Earth, and the displacement. I have the displacement here as well. But I can't find this because I don't know this one, and I'm trying to find that one. So let's look down here. Displacement on the Earth, yes. Initial velocity on the Earth, that's what I'm trying to find. Time, I don't have time. So I'm going to use this one. And this is how I know I can use this one, because if I'm going to throw an object, in this case it's a wrench. Here we are, we're going to say we're on the Earth. Okay? And here is my little wrench. There's my wrench. And if I throw it up, it's going to come up, and then it's going to come down. I know right up here at the top of its path that the velocity is 0 meters per second. So if I look at the initial velocity as when it's thrown up, right here, when it's going up, okay, I can cut this path in half, and I can say the final velocity at the top of the path will be 0. And its displacement from where I threw it from to where it is at the top of its path will be that 9 meters. So anytime you're dealing with an object that is thrown up and thrown down, this is the trick. You can always cut the path in half and know at the top, whether you're looking at the fall down or the path up, the velocity is always 0. So you can always somehow get that into the equation. So for Earth, I'm going to use final velocity squared equals the initial velocity squared plus 2 times acceleration times distance. And this is for when the astronaut is throwing the wrench on the Earth. So my final velocity, and it's going to be the final at the top of the path, is 0. The initial velocity, that's what I'm trying to find. The acceleration on Earth is, gravity on Earth is negative 9.81. And then the displacement on Earth, it went up 9 meters. It was displaced 9 meters, so we'll put 9 over here. So I'm going to do some algebra. I'm going to subtract the VI squared on this side, so I get a negative VI squared on this side of the equal sign, because I subtracted it over here, equals this mess. Get my calculator. That's going to give me 9 times 9.81 times 2 equals, that's 176.58. And remember, it is negative. Now I'm going to divide by the negative 1, on both sides, and it cancels the negatives out. So now I have VI squared equal to 176.58. So I take the square root of both sides, and my initial velocity is, let me move my camera here. My initial velocity then is going to be, put it on my calculator, 13.3. That's meters per second. Okay? So I'm just going to underline that for right now. That is my initial velocity that I threw the wrench up on the Earth. Now the question says, how high can it go on the moon if I give it the same starting speed? So now I'm going to redo this problem, but now it's going to be on the moon. I'm trying to find my displacements. So which one of these equations will I use? Well, I'm going to use the same one because I still don't know time, which I need to know for this equation, I need to know for that equation. So I'm still going to use this. But this time we're not on the Earth, we're on the moon. Okay, so I have VF squared equals VI squared plus 2AD. And I'm going to use the same path. Here I am on the moon. Draw a couple of craters on the moon, right? Some craters on the moon. And here's my wrench. And it's going to go up and down. And once again, I'm going to cut the path in half. And I'm going to know that the final velocity up here at the top of this is 0. Okay? So my final velocity on the moon will still be 0. The initial velocity will be that 13.3 plus 2 times acceleration. It's not on acceleration on the Earth, it's acceleration on the moon, which is 0.150 times that negative 9.81 times my displacement, which is what I'm trying to find. Now I'm going to do some math here. I'm just going to leave this, do it step by step. 13.3 squared gives me 176.89 plus 9.81 times 0.15 times 2 equals 2.943. 2.943, and that is a negative, okay, D. So now what I'm going to do is I'm going to subtract the 176.89 from this side, subtract 176.89 from this side. I get a negative 176.89 equal to a negative 2.943D. I'm going to divide by negative 2.943. I'm going to divide by negative 2.943. So my D on the moon, my displacement, equals, let's see what I get here. 60.1 meters. And that is my answer. Now, we're going to re-sum up what we did. So we identified we had different accelerations on the Earth and the Moon. We identified we had different displacements on the Earth and the Moon. And the connection, what connected the two together, was that it had the same starting speed, which means we needed to find the VI. So we used the Earth values to find the initial velocity that we threw the wrench up, the astronaut threw the wrench up. Then we take that and look at it from the perspective of the Moon, and we find the displacements that the wrench would go if we threw it up at this initial velocity on the Moon. So we use the Moon's gravity, and we get D equals to 60.1 meters. That's the final answer. These are multiple choice questions. So what that means is that there could be some rounding differences in between the application of these two equations. So you want to choose the answer that's closest to 60.1.